So I want to start by telling you about 3 people that have Bluetooth Low Energy devices and about ways in which they want to use these devices that intuitively ought to be possible but are actually impossible today. So Grace is a runner, and she has a Bluetooth Low Energy heart rate monitor that she uses to track her heart rate using the app Strava during her runs, and she can share that information with her coach and look at it afterwards to analyze her runs. But unfortunately, Strava's UI is a bit cumbersome to look at the current heart rate while she's running. But no big deal. Grace is a programmer, so she figures she can build her own app that just connects to the heart rate monitor and displays the heart rate in big, bold fonts. Unfortunately, she discovers that if she connects the heart rate app that she built to the heart rate monitor, she can no longer connect to the heart rate monitor using Strava. And vice versa, if she connects to the heart rate monitor using Strava, she can't connect to her app. So she can connect to one or the other, but not to both. Okay, next is Fabian. Fabian has a glucose monitor that he uses to measure his blood sugar levels. And that Bluetooth monitor is Bluetooth enabled. Okay, he also has an app on his phone that can monitor the battery levels of Bluetooth connected devices. And when he turns his phone on, the battery application pops up a notification requesting permission to access his glucose monitor. Well, this seems useful to him, right? He can get notifications when the glucose monitor is about to run out of batteries and make sure to change it before he needs to measure his blood sugar next. But he's hesitant. What if the battery monitoring application is malicious or buggy? And what if it maybe leaks information like his blood sugar level from his medical device to places it shouldn't go? And finally, Esther is just moving into a new rental place. Now, her landlord has installed a bunch of Bluetooth lights in the light fixtures, which is great because Esther hates where all the light switches are in the house. Okay, so she goes out and buys a Bluetooth Low Energy enabled light switch, and she installs it right next to her couch where she sits to watch TV. Unfortunately, after installing the switch, she realizes that because both the light switch and the light bulb are peripherals, they actually can't connect to each other, so they can't talk. So she's out of luck and out of like $60. Okay, so all 3 of these cases are actually examples of how the Internet of Things ecosystem is actually composed of these application silos, where we have peripheral devices on the bottom that connect to some sort of gateway application that exclusively owns that device. And that gateway application maybe connects to some sort of cloud service, which is again sort of tied in this walled garden with the other 2. And so we don't have much extensibility. We have no way of doing access control on which applications can access which capabilities of the peripheral, and we have a limited communication model. So as the title of the talk suggests, we focus in particular on Bluetooth Low Energy as a sort of example of this problem, and we identified 3 particular issues with Bluetooth Low Energy that limit us from building applications in a different way today. So first, with Bluetooth Low Energy, applications have to run directly on the gateway device, right? So even if all I want to do is take some sensor data from my Bluetooth connected peripheral and log it somewhere in the cloud, I still need to have a dedicated application on the gateway to translate the Bluetooth Low Energy protocol into whatever, HTTP or something. Second, only one of these applications on the gateway can connect to a particular Bluetooth peripheral at a time. And finally, that application has sort of all or nothing access. So if it can connect to the device, it can do whatever it wants with the device. And it's actually not clear sort of how to resolve these issues. Where do we put the logic that figures out how to do sharing safely and how to do access control? On the one hand, the peripherals need to be simple. And so it doesn't make that much sense to put sort of complicated logic for doing sharing and access control on these devices that need to be low cost and low power. And in fact, even if we decided we wanted to put them there, these devices are really hard to update. And so, if we want these devices to last for a long time, we're going to want to be able to modify things like access control settings or how they're shared. On the other end, the systems that are running on the gateway are oblivious to what the peripherals are actually doing. They know that they're a Bluetooth device, but they don't know if they're a heart rate monitor, or a glucose monitor, or a light bulb. And so if we don't know the functionality of the peripheral, how do we sort of virtualize it generically? And how do we expose meaningful access policies to the user? Okay, so despite these challenges, it's our contention in this work that it's the responsibility of the gateway to provide flexible and safe sharing of peripherals to multiple applications running on the gateway and running in the cloud. So we built Beetle, which is a system which is a service that runs on the gateway device, and it allows applications to safely share access to peripherals without having to explicitly coordinate. It allows users to specify fine-grained policies on peripherals and applications. It provides a many-to-many communication model between peripherals, applications on the gateway, and applications in the cloud. And it does all this in a backwards compatible fashion. So any existing peripherals and applications that use Bluetooth Low Energy work as is with Beetle, but Beetle just enables additional applications that are not currently possible. Okay, so Beetle is specific to Bluetooth Low Energy, but this is actually a problem that we see in general with gateway systems. So today, gateway systems have sort of two extreme ways of providing access to peripherals for applications. The first way is through explicit support by dedicated drivers that understand a particular class of peripherals. So maybe the most canonical example of this is something like the file system. Right? The file system provides an abstraction over storage devices, and that allows multiple applications to talk to the same storage device. It lets the user define fine-grained access policies, Unix permissions, and it's agnostic to whether the storage is a hard disk or an SSD, or if even the disk is remote. And applications don't really know the difference. Okay, so this model works really well if we know what the peripheral function is. We can provide safe virtualization and access control, but we need to have sort of a trusted module in the system for each class of devices. And this has worked pretty well in like the desktop world, where we haven't had that much proliferation of devices, but it's not going to scale to the Internet of Things, where we expect to have lots of new devices all the time. Okay, so that's one extreme. On the other end, for sort of special case devices, the system can provide exclusive access from one application to a peripheral. So this is the case for sort of niche peripherals. So on the hardware development side, we see these for like oscilloscopes and debuggers. I was at the doctor recently doing a physical, and I noticed that the thing that measures my blood pressure was connected over USB to a desktop that I think was running Windows 95. So thank God the New York medical system is like up to the 90s in computing standards. But in general, this is sort of the case for typically niche devices, but it's also the case for most IoT peripherals. And this works really well for new kinds of devices because we don't need explicit support from the system, right? We don't need to wait for the Debian maintainers to add our subsystem to Debian. But on the other hand, there's no way for the system to allow multiple applications to use a peripheral, and applications get complete control over the peripheral. So current gateway systems use some combination of these two extremes to sort of provide support for various peripherals. And so in particular, on production systems like Linux and on our mobile phone operating systems, for Bluetooth Low Energy, typically we fall in the exclusive access column, where the vast majority of peripherals are supported only by providing sort of a raw channel from only one application. And there's a few sort of minor exceptions to this, like very, very common fitness devices like pedometers. Okay, so on the one hand, we have explicit support, which I argue is not practical for the proliferation of devices that we'll see in the Internet of Things. And on the other hand, we have exclusive access, which just doesn't give us the primitives that we want. Okay, but what if there was a third option that gave us sort of the best of both worlds? That would be great. So let's look at the Bluetooth Low Energy application protocol and see if there's something in the protocol that we can use, that we can leverage to build such a system. Okay, so the Bluetooth Low Energy Application Protocol is composed of sort of two standards defined by the Bluetooth SIG. First, we have the attribute protocol. This is the protocol that peripherals use to talk to applications today in Bluetooth Low Energy. And the attribute protocol defines a data model based on attributes. Attributes are basically rows of data composed of a key called a handle, which is just a 16-bit identifier, a value, which is some stream of bytes, and a type encoded as a UUID that defines how to interpret that value. So, for example, the heart rate measurement UUID says that I should interpret the value as an 8-bit integer, and that the measurement is in beats per minute. So on top of that data model, the attribute protocol also defines a transactional flow control in terms of commands like read and write and scan for something of a particular type. In addition to that, we also have the generic attribute protocol, or GATT, which sort of imposes a structure on top of the attribute protocol. And it does this by defining a relatively small set of types that all Bluetooth applications and peripherals sort of agree on that help group related values together. So in particular, we have at the lower level characteristics which group attributes that are somehow related to the same value. So for example, the heart rate monitor characteristic, includes the heart rate measurement as well as like energy expended so far. So those are sort of related values, but they're not the exact same value. And these characteristics are further grouped into services, which are just groups of related characteristics. So like the heart rate profile has the heart rate monitoring characteristic as well as like the body location characteristic, I think it's called, something like that. Okay, so just to totally get this through our heads, here's an example communication between a heart rate monitor and an application. The application might scan for the characteristic that's defined by the type of heart rate monitor. The heart rate monitor will respond saying that the characteristic you're looking for is that it begins at handle 2. So that's a particular attribute that the application can then read to find out where the actual value of the heart rate measurement from that for that characteristic is stored. Finally, the application reads the heart rate and gets back a result. Okay. So the key insight in Beetle is that the GATT protocol is actually expressive enough to allow the system to do multiplexing of Bluetooth peripherals without having to understand what the functionality of that peripheral is. Right? We have a unified data model so the system can understand what the things on the endpoints are talking about. We have a standardized set of data types so it can understand how values are grouped together. And finally, transactions are actually meaningful at the application level. So we see this because the thing that we're reading is something like an actual heart rate that's expressed in BPM, in beats per minute, and not some like register value that I have to correlate with some other register value or something like that. Okay, so Beetle, as I said, is a service that runs on the gateway, and it interposes on the communication between applications and the peripherals. It models, so it owns all of the Bluetooth connections between the gateway and peripherals, and applications connect to Beetle instead of connecting directly to peripherals. And Beetle models all of these connections using the notion of virtual devices. A virtual device can be backed by one or more applications or one or more peripherals. And then we can allow applications and peripherals to talk to each other by just connecting these virtual devices together. So we can have multiple applications talking to a single peripheral. Because we're operating at the application layer protocol, we actually don't care what the underlying link is. So we can expose peripherals through virtual devices directly to cloud applications over a TCP connection or to other peripherals over another Bluetooth link. Okay, and the power of these virtual devices is that they really just speak GATT. They just speak the Bluetooth application layer protocol. So from the perspective of applications, a virtual device just looks like a peripheral. And from the perspective of a peripheral, the virtual device just looks like whatever gateway it was otherwise communicating with. But then internally, there's virtual devices can be used as a mechanism to provide sharing between applications by multiplexing transactions from different clients to a peripheral. Virtual devices can do access control by mapping the handle space of attributes from a peripheral to a possibly more constrained handle space exposed by the virtual device. And finally, as I mentioned, virtual devices allow flexible communication by allowing these transactions to flow over basically any reliable link. Okay, so let's dig in a little bit to how virtual devices actually implement sharing and access control. So we'll go back to Grace's example, where all she wanted to do was basically read her current heart rate from two applications, one that's going to log that heart rate to the cloud and one that's going to show it to her right now. Okay, so in Beetle, we'll just connect both of these applications to the same virtual device. Now suppose that two transactions come in simultaneously from these applications, one to read the attribute at handle 1 and one to read a different attribute at handle 2. Well, because Beetle understands where the boundaries of transactions live, it'll just process one after the other. So it will first process a request from the first one, wait for that transaction to completely finish, and only then perform the second transaction. Okay, access control is similarly pretty straightforward in this world, right? So this is Fabian's example, where we wanted to allow a battery monitoring application to communicate with a glucose monitor, but we didn't want to let it, talk to all this sensitive, read all this sensitive data from of the actual blood sugar level. So again, in Beetle, we'll just connect the application to the virtual device representing the peripheral. But instead of exposing the entire peripheral, we'll replace the handle space with a mapping of a more constrained handle space that only contains the battery level information. All right, so if the application requests to read, in this case, attribute at handle number 7 is just the battery value. Well, Beetle knows where that value is, so it'll let that request go through. But if instead it tries to read this attribute with handle 2, which in the glucose monitor corresponds to the glucose value, or the glucose characteristic, I suppose. Well, there's just no way for the battery monitor to actually even name this attribute in Beetle, right? Because the virtual device doesn't have that handle at all, so Beetle just immediately returns an error. Okay, so we've implemented Beetle for two systems, for Linux and Android. And we've used those implementations to build the three applications that I described at the beginning. Right? A multi-app heart rate monitor is just two applications. One of them is actually just Strava running natively. And the second one is this toy heart rate monitor with big fonts. You can tell that you can barely read the heart rate. Imagine reading that Strava heart rate monitor thing while you're running. Right, and if you want to see some more examples of these applications, as Jason mentioned, please come to the demo session after this talk. Okay, so we have this interposition layer. Well, what's the performance overhead? So you may not be surprised that because this interposition layer is pretty lightweight and it's really just forwarding requests for the most part, the overhead in general is quite low. So in the base case where we're just exposing one application and one peripheral to each other, just the same way that we would use Bluetooth low energy peripherals normally, there is effectively no overhead. Right? There's no statistically significant overhead that we could measure. Actually, Beetle is ever so marginally slower. And then in the case where we have multiple applications talking to the same peripheral, that's obviously dependent on the actual workload. But if it's doing read requests, we can actually cache those requests, cache the values from those requests, and get basically linear scalability. Okay, Beetle can't do everything. So in particular, Bluetooth is very Bluetooth low energy specific, right? It highly relies on sort of the semantics of the BLE application layer protocol. And so because of that, also, peripherals have to conform to sort of GATT transactional semantics. If they violate that, then Beetle doesn't work great with them. Beetle has mechanisms for providing access control, but it doesn't solve the access control problem. We still have to know how to name these devices in the first place and which kinds of policies the users might want to set. And Beetle doesn't do anything to help you actually manage the Bluetooth peripherals that you're connecting to. So for that, see complementary systems like HomeOS. Okay, so I've shown you Beetle, and I think that I've argued that the gateway is able to and should provide safe and flexible peripheral sharing that's not tied to specific peripheral device functionality. Now, Beetle does this specifically for the Bluetooth Low Energy case, but I think that as systems builders, we have to sort of strive for this more generally. I think there's also some lessons to be learned for protocol design, right? The Bluetooth Low Energy application layer protocol is very amenable to multiplexing, much more so than other application layer protocols for peripherals. And so it makes sense to sort of look at what worked so well in GATT, in the application layer protocol for Bluetooth. So the first is that the protocol defines a data model at sort of the right abstraction level, right? The pieces of data that the data model encodes are meaningful to applications. It has a standardized set of data types, and actually those data types are extensible because they're just unique UUIDs, globally unique UUIDs. Finally, I think that there are lessons for Bluetooth Low Energy peripheral builders, in particular just that they ought to keep multiplexing in mind, even if right now that's impossible. And finally, Beetle is open source and available on GitHub, and I encourage you all to check it out and use it in your projects. Thanks, and I'm happy to take questions.